Hey guys, welcome back to Functions Day 2. These are the notes for 19A. So we're going to start to go through various ways to represent functions. We can do them with verbal rules, equations, tables, and graphs. So before we begin, our input values can be represented with your x values. Your outputs, okay, would be your y values. Okay, so if we had an ordered pair, an x and then a y, input and output. Okay, but also remember that with functions, we can say our y values are also the same as f of x, okay? So f of x would represent the output for a particular input of x. So the output is 1 less than twice the input, being a verbal rule. We could say that the output f of x is actually equal to 1 less than. So there's our keyword than, so we know twice the input would be 2x, but 1 less than would be minus 1. So that would be our equation. Using that equation and that rule, we can fill out our tables. So we're saying this is 2x minus 1. So if I plug in a 1, I've got 2 times 1 is 2. I have my 2 minus 1, which is going to be 1. Okay, then I have 2 times 2, which is 4. 4 minus 1 is 3. And 3 times 2 is 6. 6 minus 1 is 5. And then I have 2 times 4 is 8. 8 minus 1 is 7. So if I graph these, again, these can all be represented as ordered pairs, 1, 1, 2, 3, 3, 5, and 4, 7. Okay. As a review, our domain would be the values. Okay, remember our domain from last class would be the values 1, 2, 3, and 4. Okay, and the range would be 1, 3, 5, and 7. Okay, if we graph these values, okay, these ordered pairs, we would take 1, 1 and put a point there. Then we have 2, 3. Okay, we have 3, 5. There's our 3, and we go up to 5. And then we're going to have 4, 7. 4, 5, 6, 7. Okay, so we represented it with 4 discrete points. If we connect them, we can connect them, then it would be a continuous line. Okay. All right, looking at the next example, we're going to change this example because it's really hard to graph. So in your notes, if you could change this to 1/2 of the input, okay, that would be great. All right, so the equation for the output is 1/2 of the input would be f of x is equal to 1/2 of the input, so 1/2 x. That can also be written like this, f of x is equal to x divided by 2. Okay, those two functions are equivalent. All right, so if we have 1/2 x and we fill out our table, we'd have 1/2 times 0 is 0. 1/2 times we're going to have, and we'll have 1 times 1/2 is 1/2. Okay, 2 times 1/2 is 1, and then 4 times 1/2 would be 2. So if we graph these points, we've got our origin at 0, 0, and then 1 to 1/2 would be right about there. Our 2, 1 would be there, and then 4, 2 would be right about here. Okay, again, this is actually the equation of a line, so we can connect the dots right here and make a line like that. Okay, now we're going backwards. Okay, here we're given the points, and we need to come up with our corresponding xy values. So I just look at my different points, and I see the first ordered pair that I have is 3, 4. Okay, then I've got 4, 3, 5, 2, and 6, 1. Okay, the rule for this, if you notice the pattern, they all add up to 7. So you can think of this as f of x is equal to 7 minus x. Okay, and if that's the case, all right, you can say the output is 7 less the input. Okay, another way to actually write it would be like this. If you had f of x is equal to negative x plus 7. Okay, if you did it like that, your rule would be the output is 7 more than the opposite of the input. Okay, those two would be equivalent. Okay, so now looking at these functions, we said before that you don't necessarily have to have f of x. You can have h of x. Remember, we say this as h of x. You're not multiplying h times x. This is just notation. So when it's saying find h of -6, all we're really doing is letting our x be equal to -6. And then we plug it in. So 3 times there's an x, so now we're going to say -6 minus 2. And then we just evaluate the expression here. We've got -18 minus 2, and we get a -20. Okay, so we can say h of -6 is equal to -20. Or we could write it as an ordered pair, -6, -20. Okay. All right, doing number 2, we're just going to let our x, in this case, our n is going to be equal to 8, okay, because that's our input value. We just look at what's in the parentheses. That's what your let statement is. Okay, so then when we evaluate, it's -2 times 8 minus 1, so -16 minus 1, and we're going to get a -17. So our g of 8 is equal to -17. Again, I can write it as an input of 8 gives me an output of -17. All right, so why don't you pause the video here and try the next two. When you start back up, I will show you the answer. So we're going to let a be equal to 8 in this example. So f of 8, so -8 plus 5 is a -3. So f, sorry, because our function is f. So f of 8 is going to be equal to -3. Again, we can write that as an input of 8 gives us an output of -3. All right, and then in the last one, we're letting our n be equal to -5. So -3 times -5, okay, plus 3. We've got our 15 plus 3 is 18. So g of -5 is equal to 18, or an input of -5 gives us an output of positive 18. Okay. All right, so another thing we're going to talk about is the zero of a function. Okay, now be careful because a zero of a function is not the same as f of 0. Okay, these are not the same. Okay, it says a zero of a function is an x value for which f of, whoops, yeah, that went away. Hold on, get rid of that guy. Okay, for which f of x is equal to 0 or y equals 0. So what that means is the zero of a function is the same as the x-intercept, okay? And what the x-intercept is where the line or curve crosses the x-axis. Recall this is the x-axis and this is the y. So just by looking at this graph, I can tell that my x-intercept is going to be -2. I'm crossing right here at -2. All right, that's my x-intercept. So, I can also figure it out algebraically by taking the function, okay, we have the function f of x is equal to 2x plus 4, and I can set that output to be equal to 0, okay, because notice my output or my y value would be at 0 to be actually hitting the x-intercept, so, or the x-axis. So if I set my output to be 0, I can then solve for x, and I can do that algebraically by subtracting 4 from both sides, okay, and then I divide by 2, my x is equal to -2. So you can tell, in this particular case, you can see algebraically, and you can tell just by looking at the graph. There's my x is -2, but it doesn't always work like that. You don't always know from the graph, and you might not have the graph available, or it might even cross at a fraction. It's hard to determine. Okay, let's try a couple of examples. So we're finding the 0. Again, finding the 0, not finding f of 0, okay? It's not the same thing. In this case, we set our output to be 0, and then we solve for x. So I subtract 1 from both sides. -1 equals -2x, and then I divide by -2. My x is going to be equal to 1/2. Okay, now you should go ahead and try number 6. So I set my output to be 0, -x plus 5. When I subtract my 5 from both sides, I get -5 is equal to -x. So when I divide by -1, my x is equal to 5. Okay, so again, that is finding the 0 of the function, not f of 0. Okay, so let's go back to our functions. Here we have two functions. One is f of x and one is g of x. Okay, number 7 says find f of 2. So this f is telling me to use the f of x function, and the 2 is actually a let statement, letting my x be equal to 2. That's my input, okay, or my domain. So if my input is 2, there's my function. To find f of 2, it's just going to be 3, and every time I have an x, I'm actually going to just put a 2. So it's 3 times x minus 1, so 6 minus 1, and I get 5. Okay, so for number 7, if you're looking at that, you're going to say that f of 2 is equal to 5. All right, or again, you can represent it with an ordered pair. An input of 2 is an output of 5. Okay, we do the next thing for g of negative 4, only now we're using this g of x function. So in this case, what's in parentheses, we're going to let our x just be equal to negative 4 because that's the only thing in the parentheses. And since our g of x function, actually write this one out, is equal to negative 5x, every place I have that x, I'm going to put a negative 4. So that's going to be equal to negative 5 times negative 4, which is positive 20. So g of negative 4 is going to be equal to 20. Okay, again, an input of negative 4 gives us an output of 20. Okay. All right, so number 9, oops, did not get pulled into my flip chart, so let's just add number 9 here. Okay, but before we do number 9, actually, I'm going to do a little side note here because this gets a little confusing. Okay, so what if I had a function, okay, this isn't in the notes, you can add it in. If I had a function that was f of x is equal to 3x plus 2, and I said, what is f of a? Well, what are you going to do? Your let statement, it seems silly, but your x is just going to be what's in parentheses. Well, what's in parentheses? Just an a. So now every time I have an x, I'm just going to put in an a. So this would become 3a plus 2. And that would be my answer. F of a would be equal to 3a plus 2. All right. What if I had another example where I said maybe g of x is equal to 4x squared plus 3x plus 1. And I said, what is g of, let's use b, g of b. All I'm going to do here is let my x be equal to b. And every place I see my x, I'm going to put a b. Seems kind of silly. Whoops, I must put an x, 3b plus 1. Okay, so every place, all I'm doing is taking what's in parentheses and substituting it in. All right, if I had f of x is equal to, oops, I made a weird little mark there. Okay, f of x is equal to 2x plus x plus 6. And I want to know what is f of a plus b. Okay, now my x is actually going to be equal to a plus b. So I go back up here and I say 2 times a plus b plus another a plus b plus 6. Notice every place we had that x, I put in a plus b. I then distribute, whoops, actually that's not 2a, okay, it's just going to be plus a plus b. Okay, plus a plus b plus c. And now I combine my like terms, 3a plus 3b plus c. Okay, so that leads us back to number 9. Okay, number 9 says, what is f of negative 1 plus 1? Okay, our f function is f of x is equal to 3x minus 1. So my let statement is only what is in parentheses. So I'm going to let my x be equal to negative 1. So every place I see an x here, I'm going to put in negative 1. So this is going to be 3 times negative 1 minus 1. okay? But I'm adding 1 at the end, outside of the function, so I'm going to add it in just like that. So 3 times -1 is -3, minus 1 plus 1. So I've got a -4 plus 1, which is a -3. So f of -1 plus 1 is equal to -3. Okay, that seems really weird, I know. Okay, we're going to try another one with number 10. Okay, so notice the difference. The only thing in parentheses here was the -1. That's why I let my x be -1. And when I use that function, only the -1 went in for the x. The 1 on the side is added in later. Okay, so now let's look at number 10. Number 10, we've got g of x minus 1. Now if you look at the top, the g function, g of x, is equal to -5x. Okay, so here, what's in parentheses? Well, in this case, my x is actually going to be equal to x minus 1. So now every time I see an x right here, I'm just going to put in that expression. So g of x minus 1 is going to be equal to -5 times my x minus 1. I distribute it, and I can say that g of x minus 1 is equal to -5x plus 5. And that's it. Okay, bye-bye.